Good morning, friends, and welcome to a new week and a very auspicious week, that of Navaratri, Durga Puja. I know it's never a good feeling to be attending a class on the morning of Shashti, but what to do? Today is the designated working day, a day where classes are supposed to be held. So we are here today, uh, and thank you very much for all of you who have joined. Um, Attendance is low today. Hopefully, it will grow within the next few minutes. Let us get started. Okay. In the last class on Saturday, we had completed our discussions and a few problems on heat exchangers using the mean temperature difference method. Okay. But then we said that there are a certain class of problems which may not be, or which is not amenable to solution by the mean temperature method or LMTD method right away, right? Um, and that is when the temperatures, an example that we say that we gave is, let us say the mass flow rates and the inlet temperatures are known, but none of the exit temperatures are known. So therefore, you cannot, unless you get all the four temperatures somehow, we are unable to calculate the LMTD or the mean temperature difference. So therefore, for such problems, but these are closed and bounded problems. These are properly framed problems. But in order to solve it using mean temperature difference method, we have to go through an iterations process, which is time consuming, which is not very friendly, especially unless you are, I mean, if you're writing a computer code, that's one thing. But otherwise, for analytical solutions, it's not amenable. Okay. So we say that, there is another type of method that people have proposed, which is rather more popular now and probably more universal or more versatile as well, which is known as the effectiveness NTU method or epsilon NTU method. So let me start sharing my screen. And remember that we had just started this method and talked about the definitions. What is epsilon? What is effectiveness? Right? Which is how we defined effectiveness is the actual heat transfer divided by the maximum possible heat transfer, Q over Q max. And how do I calculate Q max? Q max is the lower of the heat capacities, m dot Cp, the lower of the two, whether it's the hot fluid or the cold fluid, that times the temperature difference of the inlet at the inlet. Okay. So this is Q over Q max. So therefore, depending on whether the hot fluid has lower heat capacity or the cold fluid has lower heat capacity, the definitions of effectiveness varies, as we have shown here. The denominator remains the same. The numerator, we will take either the hot fluid or the temperature difference of the hot fluid or the cold fluid, so that the heat capacities in the numerator and denominator cancel out. Okay, someone's microphone is on. Can you please mute yourself? Okay. So by definition, effectiveness is less than 1, lies between 0 and 1. We are calling it effectiveness. I mentioned that, well, this is what it is called. I mean, should we have called it efficiency? Maybe, but this is the nomenclature that we follow. Okay. Here, effectiveness is less than 1. Remember, we had also studied effectiveness in case of fins, where effectiveness ideally should be more than 1. Okay. But the definitions are different, the way what we are trying to calculate are different, and so on. All right. So now let us move on and try to find out what is effectiveness. Can we get uh, an expression for effectiveness? So we will start with that for parallel flow. Okay. So let us assume, without any loss of generality, that m dot h Cph is less than m dot c Cpc. Okay, which implies that lower value m dot h Cph is equivalent to that m dot Cp of S, the smaller. So what is epsilon? You can see right from the top, we will write it in this manner. Thi minus The divided by Thi minus Tci. Okay. So now what we will do is, rest is mathematical jugglery now. Okay. See what we are trying to do. I'm going to multiply both the numerator and denominator by this term. M dot H Cph by M dot C Cpc, and also divided by agree. Now what this turns out to be is the following: Thi minus The divided by Thi minus Tci, okay, plus Tce minus Tci divided by Thi minus Tci. How am I writing this? Because remember, m dot h Cph divided by m dot c Cpc is actually Tce minus Tci divided by Thi minus The. Agree? Because m dot Cp delta T of both the fluids are equal. Okay, so that is how I could write it. So Thi, I mean this term times Tce minus Tci divided by Thi minus The. So the numerator, so that term cancels, and this is what you get. So this is my numerator. Denominator, I will keep it the way it is. So look at this, what it turns out to be. So I can just expand this one minus The minus Tce divided by just plain expansion. Okay, Thi minus Tce, The plus Tci minus Tci, all that stuff. Okay, so you get this. This is just mathematical jugglery. So why did I come to this one? Now note, from our earlier derivation, I'll show you. You can also go back when we were trying to calculate LMTD for parallel flow, we had used this. See, THE minus TCE divided by, this is parallel flow, right? This is delta TL over delta T0. This was actually exponential minus one over m dot h CPH plus 1 over m dot c CPC times UA. This we have come from earlier. This comes from earlier derivation. Let us see. I mean, is it correct? Go back quite a bit. You can go back to your notes as well. This is when, look here, we were trying to calculate the LMTD for parallel flow here. And while doing everything, sorry, my touch is, yeah, here. This expression, delta TE over delta TI is e to the power this. That's exactly what I wrote. Except E and I made it L and 0 because as we decided that we are going to use L and 0 so that we have the same expression for parallel flow and counter flow. So let's come down to where we were. Okay, so we have derived this before. I'm not writing this suddenly. Okay. So if you substitute this, we will write epsilon 1 minus exponential minus 1 plus, it would be m dot h CPH divided by m dot c CPC times. Why I did this? Because I wanted to write it in this manner. Okay. This whole thing divided by 1 plus okay. Let us term this as A. Okay. Now this we assume that m dot h CPH was the lower of the heat capacities. If we had assumed m dot c CPC to be the lower one, m dot CPS, then we would have got this 1 minus exponential minus 1 plus m dot c CPC divided by m dot h CPH times UA, exactly symmetrical. Okay, you can go through this and you will find out, divided by 1 plus m dot c CPC let us call this B. So comparing A and B, we can write generic expression. What can we write? We can write that epsilon is equal to 1 minus exponential minus 1 plus m dot cps over m dot cp L times okay. So this is my generic expression. Now, do I expect you to remember this? Hell no. Okay. But what I'm trying to show is, look at this expression now. So after looking at this, if you look into this, you can see that there are two new parameters, and both happen to be both happen to be non-dimensional. The first one, we call it the heat capacity ratio, C. And what is that? That is m dot Cp of the smaller value and divided by the larger value. Okay. So this you can remember. The other one is where the second part of the term of this method comes in. It's called number of transfer units, NTU. And what is that? That is UA divided by m dot Cp, the smaller value. Okay. So the epsilon depends on these two, primarily these two. Correct? Both parameters are non-dimensional, right? We love non-dimensional numbers. You have seen quite a few by now. And when we go to convection, you will see, you'll be just bombarded with non-dimensional numbers. One thing, of course, the specific heat ratio or the heat capacity ratio, sorry, must be less than 1 because it's a smaller over larger. And NTU must be greater than 0. So these are all positive quantities. Okay. Thus, epsilon parallel flow becomes 1 minus exponential minus 1 plus C times NTU divided by 1 plus C. Look, this is a neat expression. Again, I'm not asking you to remember this, but it is something that one can remember. It's a very neat expression that captures the performance of the heat exchanger in terms of three non-dimensional terms: the effectiveness, the heat capacity ratio C, and the number of transfer units in TU. Clear? So now, as I was telling you last time, so this expression people have plotted. You can plot effectiveness over NTU. This is parallel flow, right? If Cmin over Cmax, so this is my heat capacity ratio, capital C. So if you know the NTU and the Cmin over Cmax, you can find out effectiveness, or vice versa. If you know the temperatures, Thi, The, okay, then if you want to find out what is my effective overall heat transfer coefficient U, you find out effectiveness NTU from there. Okay. Or you want to, if you know overall heat transfer coefficient, you want to know the surface area, then also you can find out NTU. Okay. So this is how it is, and these charts, epsilon NTU charts, are very handy and useful. You have it for parallel flow, you will have it for counter flow, you'll have it for cross flow, both fluids unmixed, one mixed, one unmixed, both mixed, shell and tube, blah blah blah. Okay. In 23. Okay. So for counter flow again, we can find a similar expression. For counter flow heat exchanger, we can get a similar expression. I'm not deriving it anymore. You know how to derive it. Doesn't involve any concept or anything. It's more of mathematical jugglery. People have already done it, so no point going through it again. One is fine. You need to understand the process, but otherwise it's the same thing. And what we get is 1 minus exponential minus, sorry, 1 minus. Times NTU in the numerator, and in the denominator you have 1 minus C times exponential, and exactly the same thing, minus 1 minus C times NTU. Okay. So now, if we plot it, how do they look? I mean, you've already seen this, but the epsilon NTU charts are plotted in this manner, as you know. This is epsilon, this is NTU. Of course, it has to lie between 0 and 1. NTU can be anything. 1, 2, 3, 4, 5, blah, blah, blah. Okay. And for parallel flow, this is how. Oh, so I went above 1. Okay, so let us say this is 1. It can asymptotically reach 1. Okay. And as you increase C, this is how it is. C equal to 1, C equal to 0. And if you want to do the same for counter flow, okay, this is for parallel flow. As we saw, There the curves go something like this. Okay. Now what is NTU? NTU is a measure of the size of heat exchanger. Okay. Because UA is in the numerator. Okay. It's a measure. So if you can attain higher NTU, higher effectiveness at lower NTU, it means that it's a more compact heat exchanger. Okay. And as we see between epsilon parallel flow and counter flow, if you look at it, for a given NTU and see, the effectiveness for parallel flow is lower, that of counter flow is higher. Okay. So that's why we say counter flow, the counter flow heat exchangers are more compact. Okay. For cross flow and all, for cross flow, shell and tube, it's not possible to derive a closed form analytical expression for epsilon. Okay. So that's why we have those charts. Okay. So therefore, refer to chart. Now what we will do is we will do that special case. Okay. What is the special case? Special case is m dot Cp tends to infinity for either hot or cold side. Remember that hot, the cold fluid boiling, or the hot fluid condensing. That special case. Now, what does this mean? If the it means that the larger m dot Cp is tending to infinity. So therefore, C, which is m dot Cp smaller to m dot Cp larger, that is equal to 0. Okay. So now you have two expressions. You have two expressions, right? One for parallel flow. So can you give me the expression for epsilon? Just put C equals to 0 and tell me what it should be for parallel flow. Someone, please.
1 minus exponential of minus NTU.
Exactly. Okay, now can you please do it for the counter flow also?
The same.
Right. For the counter flow also, you will get the same. Okay. So what would NTU be? Minus log 1 minus epsilon. Right. This, my friends, as you have already seen that it is true for parallel and counter flow. This is true for all configurations. Okay, this you have to take my word. It's true for all configurations of heat exchanger, whether it's parallel flow, whether it's counter flow, whether it's any type of cross flow, shell and tube, whatever. So keep this in mind. This is important. And what happens is, if I now come to what it essentially means is, if I come to this plot, let us say, with this line, which is for 0, C min over C max, in our case, capital C, this line that is for 0 is the same for all of them. Whether it's parallel flow, sorry, why is it not moving? Whether it's counter flow, cross flow, all of these. This 0 thing, the 0 line is the same, because this is this expression 1 minus exponential minus NTU. Okay. All right. So what we will do is we will now wrap up this topic and today's lecture by solving one problem. Okay. So let's do the problem. What the problem says is, in a gas turbine power plant, I'm not writing everything. You please write it down. In a gas turbine power plant, heat is transferred in a plate fin heat exchanger. Okay. And this, you know, in gas turbine power plant, what happens? Where is the heat exchanger? Heat is transferred in a plate fin heat exchanger from the hot gases leaving the turbine to the air leaving the compressor. Right? There's a preheating before it enters the combustor, if you recall from your thermodynamics. Right? So hot gases, plate fin heat exchanger, from the hot gases leaving the turbine to the air leaving the compressor. The airflow rate is 5,000 kg per hour. So the airflow rate is 5,000 kg per hour, and the flow rate of the hot gas, which is the hot fluid, is 5075 kg per hour, almost similar. Okay. Further given, THI is 450 degrees C, TCI is 170 degrees C. U is equal to 52 watt per meter squared Kelvin, and A 50 meters squared. And Cp, you can assume it to be the same, 1050 joules per kg Kelvin for both hot gas and air. Okay. So the flow is single pass cross flow. Flow arrangement is cross flow with both fluids unmixed. Okay. What we have to do is find THE, CE, and Q. Okay. So can we do this? I think we can. Let's try. Answer. Solution rather. First, always a good idea to draw a representation. This is my heat exchanger. Area is 50 meters square. U is also given, right? Hot gases entering at m dot h 5075 kg per hour and Thi equal to 450 degrees. Hot gases exiting. I don't know what is Thg. Okay. Similarly, cold fluid coming in m dot c is 500. No, 5000. Sorry, 5000 kg per hour, and Tci is 170 degrees. And here again Tce, I don't know. Okay. So this is a problem where the inlet temperatures are known, exit temperatures are not known. So therefore, I cannot calculate Q, I cannot calculate LMTD immediately without going through trial and error. I can calculate ratios. I can calculate what is THEO minus THI, sorry, THI minus THE over TC minus TCI. What is the basic temperature changes of both fluids? That ratio, but not the exact temperature change. Okay. So what we will do is, this is a problem that needs to be solved by epsilon NTU method. So remember that any problem that you can solve by LMTD can also be solved by epsilon NTU. That's a more or less generic statement. Okay, but not vice versa. So let us calculate C. What is capital C? Smaller into larger. The specific heats are the same. So 1050 and this is 5075 by 1050. 1050 is na? What did I write? CP? Yeah. So this is almost equal to 1.985. Okay. Do I know NTU? Yes, I know, because UA divided by m dot CPS. So that is given 52 times 50. You have to be careful about the units. Huh? 52 times 50. 52 was watt per meter squared Kelvin, and 50 is meter squared. So that's okay. Watts per Kelvin in the numerator. Denominator, however, you have to convert to SI units. I have given you as kg per hour. So please convert that kg per second. Okay, so m dot is 5000 by 3600 times 1050. This is important, huh? 3600 is important. This turns out to be 1.783. Okay. So from epsilon NTU plot for cross flow with both fluids unmixed. Okay, it is important to recognize or identify. Okay, so let us go here, and we have to read out of the chart which is not a big problem. This is the chart. Okay. What was my C? Was almost close to 1, right? 0.985. So almost close to 1. You have to do a little bit of interpolation, but that's okay. And NTU has come out to be 1.78. 1.78. Let's say 1.75 here. Okay. So if I don't know if you can see my cursor. If I just go up here and go to 1, yeah, it's about to do a little bit of eye estimation and extrapolation, but it turns out to be, we get epsilon was equal to about 0.6. Okay, once more, we're looking at this one. If you come here, a little more than 1 and 1.78, yeah, so it's about 0.6. Correct. Now, what do we have to find out? We have to find out TCE, THE, and Q. We're not done yet. Epsilon equal to 0.6. Then write a note, need a bit of extrapolation or interpolation. Sorry. So what does this mean? Epsilon also means TCE minus TCI because here it was a cold fluid that had the smaller heat capacity. So this is 0.6. We know everything. We know THI, we know TCI. TCE is the only unknown. So it turns out that TCE will be 338 degrees C. Okay. So Q, m dot C, CPC times TCE minus TCI, right? So 5000 by 3600 times 1050 times 338 minus 170. This turns out to be 245 kilowatts. TC done, Q done, THE. Okay. Q is also m dot H CPH THI minus THE equals to 245 kilowatt. So this implies THE turns out to be 285 degrees. Okay, these are my 3 answers. Okay, I could have calculated THE other way also. I mean, I could have gone by the ratio of the temperature drops or temperature differences. Okay, so you understand how to solve this problem using the epsilon NTU method. Okay. So that kind of brings us to the end of our discussions on heat exchangers. As I said that I have already uploaded the problems, so you should be fine with that, and you should be able to solve most of them. Okay. Now, just on a parting note, please keep in mind that heat exchanger design is not just Q equals to UA delta T. Okay. What we did was this very fundamental stuff. But an actual heat exchanger design depends on a lot of things. Okay. For example, what is the pressure drop on both sides? We don't know. We are just saying, okay, some m dot is coming and leaving from the other side. There's a tubular arrangement. But how am I making them flow? Of course, I need a pump, right? If it's liquid, or a compressor, or a blower, if it's a gas. So what about that pumping power? needs to be considered, right? Size restriction. Okay. Size restrictions. Now you may say, okay, if you have size restriction, I think it's a given that you go for a compact heat exchanger and therefore go for counterflow. But just the streams that are available in the plant may not allow you to go for a counterflow configuration. What if both the hot and cold fluids are coming from the same side? Are you going to, then you will have to go for a long plumbing line to bring it from the other end, right? So then it doesn't remain compact anymore. The heat exchanger may be compact, but all these accessories and the other paraphernalia that you have to do, you have to consider those the space occupied by those as well. Okay. Stress considerations, right? And if I'm having a high flow rate, and what is the pressure that is generated? Can the walls of the heat exchanger withstand that pressure? Okay. Materials used, corrosion, erosion. If it's hot fluid, there is fouling. We have talked about that, etc. Service requirements. These needs to be periodically cleaned, serviced. If something goes wrong, so you have to come up with that kind of a design. These are all practical considerations. And finally, last but not the least, the king or the emperor in any consideration, any engineering product, and that's cost. Okay. Cost is king. All right, so we did not consider all that, but what I'm trying to tell you is, it's just this final heat exchanger design depends on so many things. These calculations, of course, are very, very important, because unless you have these right, then you are not going to get the type of heat exchange that you're looking for. But you must consider all these other constraints, and therefore your final design may not be the most optimal that these calculations will tell you. Okay. All right. So with that, I wish you all a very nice puja break, and I don't want to burden you with anything here. Just go through these notes and maybe the problems. And one more thing that I will do is, I will try to upload, or I will upload, some handwritten notes on review of fluid mechanics. Please go through them. It's a simple reading of a few pages. Go through them and make sure that these concepts are coming back to you, because we don't have the time to spend on review of fluid mechanics. But I do know that you have taken it more than a year back, so in your second year, so not every concept is fresh in your mind. So this will be a bit of a refresher. Okay, especially viscous flow through a pipe, flow over a plate, all that you have learned about the skin friction coefficient and Reynolds number. What is turbulence? What is laminar flow? What is turbulent flow? So these are the things that you need to brush up. These are the concepts that we are going to use regularly in convection, which is what we are going to start from next week. So please do this refresher, and what I will do is I will try to just upload a few pages, and you will be able to go through them. Okay. Thank you very much. Have a very nice break, and hopefully when you come back next week, you will all be charged up as so would be. And then it's just another month, the last lap of this semester. Okay. All right. Have a great week, and see you again next Monday, which I believe is 18th of October. Okay. Thank you. Cheers.